All right, so continuing on with looking at solids of revolution using the disk method. To refresh, we are looking at either a horizontal or a vertical axis of revolution, and this formula comes from the area formula for a cylinder, which is volume equals pi r squared h. Well, h is the width of our disk. R is going to be the height of the rectangle because, again, when we rotate this rectangle around, it's going to make this larger circle, which is why that just becomes the radius. And the pi is just a constant, so that's where that's coming from. So our focus on this section today is going to be setting up the integrals. On your homework, you're going to go ahead and evaluate the integrals, but I am not going to spend time on the notes just for the sake of time working through the integrals on these today. We're just going to practice with setting them up. Now, on all of these examples, the graphs have been provided for you. If they are not, rule number 1 is you need to draw it out. That's been the question you guys have been asking over and over again. How would you do this if you didn't have a graph? Well, it's very difficult if you can't see an image of what is happening. So the first thing you do is you get out your graphing calculator or you get out a piece of graph paper and you sketch this out yourself. And you always want to sketch this representative rectangle because that is how you're going to define your volume formula for the disk kind of in general. So that's going to be really important. So this first one, we want to set up the integral, we're not going to evaluate today, that gives the volume of the solid formed by revolving this region about the x-axis. So we want to use the graph of y equals 4 minus x squared, that's the upside down parabola piece, x equals 0, and y equals 0. So that's the horizontal and the vertical axis. So that gives us that blue shaded region there. Now, this rectangle is what we're going to use to figure this out. Now, it doesn't matter where you draw the rectangle. It's just kind of in general what we're looking at. This value here, the height of this rectangle, is going to be r. Now, to get to this height of anywhere on the function, that's going to be the value of the function itself. So r of x is going to be 4 minus x squared in this case. That's the height of the rectangle. That's just like what we've done with Riemann sums and anything else. So to set this up, that's all we need is the radius. So the volume formula is going to be pi times the integral from, in this case, since this rectangle is perpendicular to the x-axis, we're rotating about the x-axis. We know that we want to do our integral dx. So we're going to go from 0 to 2 of r of x, which is 4 minus x squared, because, again, it's radius squared to find the area of a circle, dx. That takes care of the width of the disk. And so we're basically adding up infinitely many disks with a width that is approaching 0 and a radius of 4 minus x squared. And so you can work that out and get the answer. But that is how we would set this one up. Let's look at another one. So this time our equation is the square root of 4 minus x squared. Again, we're bounded by x equals 0 and y equals 0. And so we need to figure out the height of our representative rectangle because that represents our radius. And again, you could really draw that rectangle anywhere you want. It does not matter. So to get the height of the rectangle, that's going to be our formula, or the equation that we were given. So r of x is going to be equal to the square root of 4 minus x squared. Since we are rotating about the x-axis, that tells us our integral needs to be dx. So we want to go from 0 to 2 using our limits of integration this time. So the volume would be the integral, I forgot my pi. Pi times the integral from 0 to 2 of the square root of 4 minus x squared dx. And now you can simplify that from here, and if we were going to evaluate this, then we definitely would. But a word of advice, if all it's asking you to do is to set it up, then plug in all the pieces and move on. There's no reason to do any more simplifying. And in fact, like if I was trying to grade this, I would rather see it unsimplified because it helps me see exactly where all the pieces are and where they came from. When you guys do simplifying on these that are just a setup, then I have to kind of work backwards from your answer to make sure you plugged everything into the right places. Let's look at one where we are going to go around a vertical axis. So example 3 says, set up and evaluate the integral that gives the volume of the solid formed by revolving the region about the y-axis. Now we're going to again go ahead and assume because of the picture that we're bounded by the x and y-axis as well. So it's this quarter circle, which is what we have here. And this time, since we're rotating about the y-axis, that's how I know that my rectangles have to be perpendicular to the y-axis. And I also know that this time I need to set up my integral dy, which means my limits of integration are going to come from the y-axis. So we need this equation to be r of y. Right now, this is set up as a function of x. Y equals something with x. So we need to solve this. So we'll start by squaring both sides. Y squared equals 16 minus x squared. And then we subtract 16 and divide by -1. So we end up getting 16 minus y squared equals x squared. And then we'll go ahead and take the square root, and we're going to get plus or minus the square root of 16 minus y squared. However, looking at the region that we have, plus or minus would give us the top half of the circle, and it would give us the back side of the circle here. But since we only have the right-hand side, we're only interested in the positive side. So, oops, I don't need that squared. So that's the equation that we're going to use, the square root of 16 minus y squared. We don't need the negative part because it's not part of our region here. Okay. Okay. So now this is our capital R. That's going to be our radius. And so the volume is going to be pi times the integral from the y-axis boundaries are 0 to 4 of the square root of 16 minus y squared dy. So it's just a matter of deciding whether your integral needs to be dy or dx, and it has to do with which axis you are revolving around. If you're revolving around the x-axis, then you are going to use a dx integral. And if you're evolving around the y-axis, you're going to use a dy integral. Okay, so I'm going to pause this for a second, and I want you guys to try and set up example 4. It looks like we're going around the y-axis, so you want a dy integral, and it looks like our radius is already defined as a function of y, so we don't need to do any rearranging. Notice, however, that our region that they've got shaded in there does not go all the way down to 0. So take that into account when choosing your limits of integration. Pause your video, try this one yourself, and I'm going to reveal the answer in 3 seconds. Here it is. So again, we're revolving around the y-axis this time, so that's dy, and that means that our limits of integration need to come from the y-axis. So we have pi times the integral from 1 to 4 of the radius, whoops, I forgot my squared, the radius squared dy. And if you evaluate that integral, that's going to give you the volume of this figure. You can kind of imagine this almost looks like one of the little tops of the Taj Mahal, I feel like, is what this would kind of look like here. This like pointy, eggy shaped dome kind of thing. Okay. Now, let's look at one that uses a different axis of revolution. Now, this is the same kind of figure that we looked at in, was it this one? Yes. This simulation that I showed you on the first video. So we're going to rotate over this vertical line here. So our radius is always measuring from the axis of rotation, not necessarily the x-axis. So we're going to rotate around. I've got my discs turned on. Let me turn those off. But you can see that the radius is going to be from the line where it stops out to the outside of this region. So that's a little bit different. So we need to really count on our representative rectangles here. Let me show you how this would work. So we want to set up and evaluate the integral that gives the volume of the solid formed by revolving the region about the line y equals 2. First thing we have to decide is y equals 2 is a horizontal line, which means that our integral needs to be dx, because if it's a horizontal line, our rectangles are going to be perpendicular to that, okay? And you can see that in the picture here. Now, because we're revolving around this line here, not the x-axis, that means our radius is just going to be this. The problem is this function y equals 4 minus x squared over 4 is always going to give me the height from the x-axis all the way to the top. That's too much for my radius. We don't want that much. And so we have to essentially subtract off this bit here. It is exactly like before, top curve minus bottom curve. So in this case, the top curve is 4 minus x squared over 4. The bottom curve is y equals 2. Okay? And so the radius in terms of x is going to be the top curve, 4 minus x squared over 4, minus the bottom curve, which is 2. And again, you can simplify that if you want. So that's going to give us 2 minus x squared over 4. That's the radius that we are going to use because it only needs to be the width of the piece that we are rotating. Okay? Now, to set up our integral, you can go ahead and set it up. So see if you can choose the correct limits of integration. See if you can set up this formula correctly. Pause your video and come back in 3 seconds for the answer. And there you go. Now, again, because this is a dx integral, that means our limits of integration need to come from the x-axis, which is why I chose -3 to 3 for my limits of integration. Final word of warning, the biggest mistakes that I tend to see is people forgetting the pi. That just comes from the volume formula for a disk, so you got to have the pi in there, and it can be inside the integral or outside. It's just a constant multiplier. And forgetting to square the radius. Those are the two errors that I see pretty commonly. So that is how you can use the disk method to find the volume. Now, in the next video, we're going to extend this just a little bit further. In this example here, we rotated this figure around the line y equals 2. So there was no gap when we rotated it. If I were to rotate this about the x-axis instead, that's going to change things. Can you imagine if I took this figure and rotated it around, you would end up having a hole in the middle of it where there was nothing. We would have the same shape down here all the way around, but it would be empty in the center because part of what we rotated was empty space. And so that is going to change our approach, and that's what we're going to work on in the third part of this week's information.